time to make our theorizing and conjecturing and guessing about tangent line calculations more official, and introduce some terminology, and in particular the terminology of limits. Okay, so if we want to find the slope of the tangent line to y equals x squared, I'll do y and x instead of y and t, although we often want to think of t as of x as time in a lot of practical problems. At the point, let's say x equals 2. Okay, so I've graphed x equals 2, y equals 4, and then I want to look at the tangent line. We know the process is we look at these secant lines, and then we try to find the trend as these points get very close to each other. And you can see it stabilizes, and it looks like there's some well-defined line, and we want to know how to make that more official and really calculate it precisely. Okay, so let's go back to here. Alrighty, want that slope. And we know a process, and we just want to have a more official name for that. We take 2, and when we add a little bit to it, like 0.001, and we plug it into the function, and then we compare it to 2 itself, and then we divide, that's the rise, and then we divide it by the run, 2 plus 0.01 minus 2. Now, of course, that can be summarized a little bit. Let me just copy and paste, and the 2's cancel here, and we just get this amount. Okay, so let me introduce some notation here. We've got our function f of x is x squared, and we've got this little wiggle in the x. That's often given two different names. One very descriptive name is delta x. That is to be read as a change in x, and usually a small change. A delta, if you ask an engineer, what's the delta today? It's like, that's the change, and it's usually supposed to be a small change, sort of tweaking things. Okay? And that, in this case, in the example above, it's 0.001. But that's something we get to choose, and in fact, the process we've gotten is choosing many different delta x's and seeing what the trend is as that changes. Delta y, oops, wrong delta, capital delta. It looks like a triangle, but it's a capital, Greek capital D. It's a capital delta. That's the change in the y value, the output, as opposed to the change in the input. Now, there's a huge difference between these guys. The delta x, let me put in here, this is something we get to choose. And the delta y is something we have to calculate based on the function. Okay. And so let's see what's going on here. This is just delta y over delta x for a particular choice of delta x, where that's 0.001. And so the delta x is pretty simple because we chose it, and that's what happened with the canceling out here. And then the delta y, though, depends on exactly what this function is. Okay. So what are we putting in? Let's see what the general form is. We're taking a function, here it's f of x equals x squared, and we're plugging in 2 plus delta x, and then we're comparing it to what happens if we didn't add in the delta x at all. And then we're dividing it by delta x. There's going to be various different variations on this, but this is the usual form of a difference quotient. We've got a difference on the top, and it's really a difference on the bottom. It's the difference of the two x values, but it canceled out to be just the change, because we actually chose the change, the difference, to be delta x and named that. And so that's what we're often going to be doing. So the 2, of course, is because we wanted this x to be 2. And we could make that a variable as well in a little bit, but let's just leave it as 2 right now. Okay. And the tricky thing here is not so much this part. This is just kind of introducing some notation to what we've always been doing. It's this whole thing about the trend. Okay, where we choose delta x to be smaller and smaller values, and we try to guess the trend. Can we get out the guessing part? Well, the official name for that is we just take this expression. This is something that where delta x, this quantity delta x, is our variable that we get to choose. And what we did was we took that smaller and smaller, and we tried to figure out what happens as that approached 0. And so the way we write that is we take the limit as delta x, and then a little arrow approaches 0. Okay, so this is our terminology for what we've been doing. We take this expression, which is the slope of the secant line, and we're taking the limit as delta x goes to 0. And what this says is just exactly what we've been doing. Take all possible values of delta x in principle and look to see if there is one fixed value that this expression is getting closer to, let's say closer and closer to, as delta x gets close to 0. We could say that more precisely, but believe me, you really don't want to see it. It's a more official, more abstruse kind of mathematical thing than most people want to see. It's not even in the BC syllabus anymore. It's lovely if you want to be a mathematician, but that's maybe not most people's goal. Sad to say. So let's look at in this particular expression with the function being x squared. What the heck is that going to do? So far we've just introduced notation. I'm not sure if this is going to help us at all. Now here the function that we're taking is just the squaring function. So let's put that back in. Okay, 2 squared. Okay, well we can actually at least get somewhere here. We don't know how to deal with this limit of thing yet. So let's just leave it alone. But we can at least manipulate this expression a little bit. It's a quantity squared. So what we're going to get is just 2 squared here, which is 4, plus 2 times delta x. Okay, well that's just 4 delta x, plus delta x squared. I'm going to put that in parentheses. The thing about delta x, it's a very descriptive terminology, but it's hard to remember that it's just one quantity. It's not a quantity delta times a quantity x. It's just one variable. There's other letters, like often h is used instead. And I don't know, I decided to use delta x for this video. Okay, so now one thing we notice is the 4's cancel. Haha. Okay, let me do that. Oh, first let me put an equals here. Okay. Okay. So that's nice, and that's actually especially nice. It's not just an accidental slight simplification, because now there's another cancellation that can happen. Hey, look at that. We've got a common factor of delta x on the top and on the bottom. So let me be really careful about that. Let me factor out a delta x on the top. Okay, I'll put a 4 in there. Okay, I'm factoring out. It's got to be a common factor. It's a huge mistake people make. Now that the 4's have canceled, it's a common factor of delta x on the top, and only an absolute universal common factor can cancel top and bottom, but it does. And now we're down to a pretty simple, limit calculation. We're looking at what would happen if I take a bunch of different numbers at delta x, I add 4 to those numbers, and then I let delta x go to 0. What's going to happen to these numbers? Well, if delta x is getting smaller and smaller, getting closer to 0, then 4 plus that number is almost certainly getting very, very close to 4. So let me talk about just a minute again. I don't want to make this too long. But what's amazing here? What if we had just tried to say, oh, you know, it wasn't that hard to do this final step where we evaluated a limit. We just got a bunch of numbers. Imagine delta x is like 0.001, and then 0.0001, and 0.000001. You're just going to get 4.01, 4.001, 4.00001. It's going to be obvious that they're going to 4. And nobody in the world would deny that. And it's easy to prove even if you want it to do this all rigorously. Okay? So that was not that hard to calculate that limit. Why couldn't we have just done it here? Why couldn't we have just observed that here? The reason why these steps of algebra are really crucial is that you've got a very confusing situation here, and it's on purpose. Remember what's going on here. We've got the delta x is the difference in the x values. So that's a line down, a segment down here. The delta y is the difference in the y values. I should have drawn in the triangle, but I'm lazy and I don't want to make the video longer and have you watch me do that. So the delta x is here, the delta y is here. The whole point was they're both getting very, 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 very small. And so what's happening in this quotient is the bottom is getting very, very close to 0. The top is getting very, very close to 0. When delta x is small, 2 plus a little small squared minus 2 squared, that's going to be very close to 0 because these two quantities are close to each other. But the real problem is in the bottom going to 0. We can't divide by 0. And so when the denominator even gets close to 0, it's dangerous. It's interesting, and it's the whole name of the game, because we're always going to be doing that when we're finding slopes of tangent lines. But it means that you can't manipulate these expressions. You can't just take the limit very quickly and directly. What we're going to have is a two-stage process where we do some algebra at the start and then finally evaluate the limit at the end. And so we're going to have to justify this a little bit more. But the main thing I want to get out of this is an example of really calculating this guy and being sure it's 4, as opposed to having to use calculators and guessing, and also illustrating this mixture of the definition, the idea of a limit, which is a terminology we're going to be using from now on, and certain kinds of algebraic manipulations that we're going to have to do inside the limit. So we actually even want to go back even a little bit before this, and we're going to do examples of limits just on their own. That's something we're going to need to do. Not necessarily for a tangent slope. There's lots of other uses of limit, although that's our main one, our motivating one so far. Okay, and we're also going to need to do eventually some other concepts that come up very naturally out of limits that don't necessarily have to do with tangent slopes. But this is where we're going to come to as our killer app for limits, is figuring out tangent slopes. That's plenty long.